Hello, this is the first video of Game Theory Series 2 for OCR Discrete Further Mathematics and considers 3x3 zero-sum games. In the Game Theory Series 1, you were introduced to zero-sum games, and the payoff matrix represents the winnings from the point of view of player A. Also in Series 1, we looked at optimal mixed strategies for each player using graphs, remembering that in a zero-sum game there is no collaborative strategy that benefits both players. So here is an example of a payoff matrix for a two-player zero-sum game. Remember that this shows the winnings from players A point of view. If we wanted to see the situation from player B's point of view, then it would be the negative of each of those cell entries. So, for example here, if player A plays strategy P and player B plays strategy X, A would lose 4, but B would win 4. In Series 1, we saw how to find pure and mixed strategies for 2x2, 2x3 and 3x2 games. We now move on to looking at 3x3 games, which as you can see is the case here, with player A having their 3 strategies or options PQR and player B with 3 strategies or options XYZ. First, we need to look for a stable solution. Hopefully you remember the row maxi-min and the column mini-max. So I'm looking across the row for A playing strategy P, and I choose the minimum, which is -2. Similarly, across row Q, the minimum is 1, and for row R, the minimum is 2. Looking now down the columns for player B, I'm looking for the maximum score, which would be a 5, a 2 and a 4. So for these row results, I'm looking for the maximum value of those minimum, which in this case will be a 2. And for the column, I am looking for the minimum of these maximum values, which also happens to be a 2. Therefore, the row maxi-min in this case equals the column mini-max, and I do indeed have a stable solution. If I'm looking for the play safe strategy or the least worst option for A, this is going to be R. And for B, this will be Y. Therefore we say there is a saddle point at RY, and the value of the game for A will be 2, and for B will be -2. So when there is a stable solution, then is what we call a pure strategy. Players will always play their play safe strategy. In other words, if player A and B know that the other player will play safe, then there is no incentive for either of them to change strategy. In these two examples here, we can see by looking at the row maxi-min and the column mini-max shown in red that these are not equal, and therefore these games do not have stable solutions. Hence there are no pure strategies, so we need to look at mixed strategies. You may remember a mixed strategy is where a player chooses to play each of their options or strategies, PQ or R, X, Y or Z, with a probability greater than or equal to 0, therefore to be determined. If player A knows player B will play safe, in other words the X, then A would choose to play Q, because then they would lose nothing, rather than playing their play safe strategy of P. Therefore A may wish to consider varying playing P, Q or R for a portion of the time. In Series 1 we also met the idea of dominance arguments. So before we look for a mixed strategy, we should consider dominance, as this might reduce the problem of 3x3 zero-sum payoff matrix to a lower order game that is then easier to solve. So let's look at both rows and columns in these examples of payoff matrices. Starting with the left-hand game. Let's start with the rows. Well, if we compare P and Q, we can see that -2 is worse than 0, but 1 is better than -1. So P and Q, there isn't going to be a dominance argument. However, if we compare P and R, we can see that -2 would be better than -3, that 1 is better than 0, and 2 is better than 1. And therefore we would say that P dominates R. And that is to say that A should never play R, because it's always better to play P. And therefore this would reduce down to a 2x3 zero-sum game. On the right hand side, if we compare the rows, no row dominates another, and the same with the columns. Hence, in this particular example, we cannot reduce. So, for the payoff matrix on the left-hand side that we have reduced to a 2x3 game, we could now solve this using graphical methods, as shown in the previous game theory series. On the right-hand side, though, we have not been able to use dominance arguments to reduce the 3x3 payoff matrix, and so we can't use graphical methods and we need a different approach. The technique we're going to use is to formulate the game as a linear programming problem. You will note that there is a separate video series on linear programming. However, in the next video we will see how to formulate a m times n zero-sum game as a linear programming problem.